Ahoy, class. Hope everyone's doing well. Good morning. Hola. Wow, we went from 11 people to 7 people. Got a pretty straightforward lesson for you today. Should be a fun time. All right, I don't feel like waiting. I'm just going to get started. So, who didn't like the Ahoy? I liked it. So, so that was kind of the last lesson where we talked about the Standard Model, about atomic physics and nuclear physics, and subnuclear physics. And so we're going to move on to the next unit, which is energy production and climate change. Okay, so this is SL41. And so we are going to start talking about energy production. Well, today's lesson is just going to be about energy production. Okay. So the first thing that I want to talk about in energy production is excuse me. I had this weird morning where I woke up at like 5:30 and I felt like really energized at 5:30. And then I was like, it's too early. I'm going to go back to sleep. And then I woke up at 6:30 and I felt horrible. Does that ever happen to you guys? So what I want to talk about first is sort of non-renewable energy production. Okay, so that is like fossil fuels and things like that. So basically, if you have non-renewable energy production, you are usually burning some kind of fuel. Okay, and so the question is, how do we characterize the fuel? Okay, and so there are kind of two key parameters when we are discussing fuel. Okay, so one of them is called the energy density. Okay, and the energy density is equal to the energy released by burning the fuel. So it's going to be in the form of heat, divided by the volume of that fuel. That was burnt. Okay? So, you could also talk about energy density in the context of like batteries. What is the energy density of a battery? Units of energy density are joules per cubic meter. Okay? So, why is energy density important? That is whenever you have a small amount of space where you need to do something, then energy density is going to be really important. So, for example, in a car, okay, you want the car to be small so that it's aerodynamic. And so you want to fill the car with a fuel that has a high energy density. We can fit a lot of energy into the fuel tank, right? Because the volume of fuel is basically the volume of your gas tank. So we want to put as much, and the size of the gas tank is sort of determined just by, the design of the car itself. So we want, in order to allow the car to have the greatest range possible, we want to fit as much fuel into that gas tank as possible. So we want to use a fuel, with a high energy density, of which gasoline happens to have a pretty high energy density. Wood has a lower energy density. That's why we don't shovel wood into cars, okay? And use wood to run them, among other reasons. But oftentimes, so energy density, you're almost, even though the metric unit of energy density is joules per cubic meter, more often you're going to see energy density measured in megajoules per cubic meter. Okay, so that's just a more common, because the amount of heat that's released is a lot greater than 1 joule. So oftentimes this is megajoules, which mega means millions, and so that is, of course, 10 to the 6th power is a million. So energy density is important. Then there is something called specific energy, which is sort of analogous to energy density, and it is equal to the energy released by burning fuel divided by the mass of the fuel that was burned. Okay? So, specific energy is going to be really important for things like airplanes. Okay? Because airplanes, things like rocket ships, anything where you have to lift something vertically, you want to do that with as little energy as possible. So you want it to be light. You want the fuel to have a lot of energy pound for pound. And so this drives the choice of rocket fuel. You want a high specific energy. If we think about satellites, oftentimes NASA satellites will use plutonium to run the electronics in the satellite, in the space probe. And the reason is that plutonium has an incredibly high specific energy. And so plutonium is able to run a satellite for a long time before it will run out of energy, and it's very light. Compared to the amount of energy it provides for its mass is a whole lot. And so what that means is, because if you have a space probe that's going to Saturn, it takes a lot of energy to get the probe to Saturn in the first place. So we want to make, and we can't refuel it, so we want to make sure that it lasts as long as possible and that the satellite is as light as possible so that it's easier to get to its destination. Units of specific energy are joules per kilogram, okay, or megajoules per kilogram. All right. So there you have it. Now, the work. So remember, the heat. This is when you burn fuel, you get heat released. You get heat released. Okay. So, and then that heat is converted into work, and work is basically useful energy. Okay, heat is a hard energy to control. All right, heat dissipates. It flows in a certain direction that you don't want it to flow, and so when you convert heat into work, there's always going to be an efficiency factor, okay? And so the work that you get is equal to the efficiency times the heat released by burning the fuel, okay? So for example, if you wanted to know what is the heat released by burning a certain mass of fuel, then you would take specific energy has to do with mass, right? So Q is going to be specific energy. So just multiplying both sides by mass, the heat release would be specific energy times mass. If we talked about burning a certain volume of fuel, you would talk about the energy density, and we multiply both sides by volume. We get energy released as energy density times volume. Okay, so that is how you would calculate the heat in this equation. The efficiency is usually going to be a given, or it's going to be related to the Carnot efficiency. So I talked about because of the second law of thermodynamics, entropy must increase, and so that limits the efficiency of heat engines. And so the efficiency, sort of the maximum efficiency, is equal to 1 minus the lowest temperature divided by the highest temperature in the heat engine. Okay. So, yeah, I might just say the efficiency is 20%, or I might say it's a maximum efficiency Carnot engine or something like that. Okay. So that is how you calculate the work done by some method of energy production. So that's kind of nice. So now what I would, and I think that this is simple enough that I'm not going to really do examples today. I think you guys can figure it out. So now let's talk about a little bit about, so this was non-renewable energy production. Let's talk a little bit about renewable energy production. And so we're going to talk about two different ways of renewable energy production. One way is solar panels. Okay. So solar panels, here's a solar panel. It has a certain area. So given the length and the width of the solar panel, it has a certain area, which is equal to length times width. Okay? And then the sun is hitting the solar panel. Okay? And there is a thing called the solar constant. S, all right, which is equal to the luminous energy, or I'm going to say luminous power So remember, power is energy per time. Okay. And so, the longer the sun is giving us energy at a certain rate. Okay. In other words, if you lay in the sun for a longer amount of time, you've absorbed more energy. So there's a certain amount of energy per time that we receive from the sun. Divided by the area. Here comes the sneeze. Yeah! So it's energy per area per time. All right. So energy per time is a watt, and area is measured in meters squared. So the units of solar constant are watts per meter squared. All right. And so we could also think about it as power per area. Power per area. So with a solar panel, the solar constant is, you can see that if I take the solar constant and I multiply it by area, I get the power. Okay? So power output of a solar panel is equal to solar constant times the area of the solar panel. And I want to point out that this is actually the cross-sectional area. Okay? So it depends on, so this is cross-sectional area. What if, you have a solar panel like this, and what if the solar panel is edge on to the sun? Then the cross-sectional area is basically zero, or very nearly zero. And so that solar panel is going to output basically no power, okay? If it's at an angle like this, okay, the cross-sectional area is like the area that it presents to the camera. So this is obviously less than so it's just this area of this outline, right? So in order to get the full area, you have to have the solar panel directly pointed at the sun. Okay, so it matters. When I say cross-sectional area, I mean the area that, maybe I should say projected area. So what is the effective area taking into account the angle of the solar panel to the sun? And then, of course, there is an efficiency factor. Okay. Now, solar panels are not heat engines, so they are not bound by this equation, but they are bound by their own rules. Solar panels are generating energy in a quantum mechanical way, so that has its own issues and its own sort of limits to what it can do. And the efficiency of a solar panel is around 10 to 20%. All right, 10 to 20%. So this is the power output of a solar panel. Now, the solar constant can fluctuate. So it depends on altitude, because if you are higher up, you have less. So if you are in space, the solar constant is greater than if you are on the surface of the Earth. If you're on the surface of the Earth, then the atmosphere is blocked. Even though it doesn't look like it, the atmosphere actually is blocking some of the sunlight. Okay, it's absorbing some of that sunlight. So by the time it reaches our elevation, the solar constant is reduced from what it was above the atmosphere. Okay, so the solar constant at the surface of the Earth is right around 1,000 watts per meter squared, but the solar constant up above the atmosphere, if you were in outer space, is about 1,400 watts per meter squared. Okay, so the solar constant depends on distance, on the atmosphere. It also depends on the weather. If there's a giant cloud over the top, then obviously that's going to affect the solar constant. And it also depends on a planet's distance from the sun. Okay, planets that are closer to the sun. So, for example, if you had a solar panel on Mercury, because Mercury is closer to the sun, it experiences a greater solar constant. Okay, and so solar panels are going to be much more effective on Mercury than they are on Earth. Similarly, if we take a solar panel to Mars, Mars is further away from the sun than Earth, and so the solar constant is less on Mars. So you have less energy from solar panels. NASA scientists have to take that into account, right? We drop a rover on Mars, and it's being run by solar panels. We got to make sure that the area of those solar panels is enough to power the rover, given where it's going to go. It would have more than enough if we took that rover to Earth, where the solar constant is bigger. Okay. All right. The other method of energy production is wind turbines. You could even have, in a dam, you have water is falling. So wind is the flow of air, and you're using the flow of air to spin a propeller, essentially. All right. The way a dam works is it uses the water is elevated. It loses gravitational potential energy and gains kinetic energy. So you're using the flow of water to spin a propeller. Okay. So it's the same method, the same, slightly different technology, but it's the same idea. It's just a different fluid that's spinning the propeller for wind versus hydroelectric power generation. All right. So let's suppose you have a wind turbine, and so it kind of looks like this. They can have different numbers of blades, and here's the wind is coming in. All right. Now that's going to make the blades of the wind turbine spin, and you can imagine that as a result of that, the blades of the wind turbine are sweeping out and making sort of a circular area. Okay. So we'll call that area A, and it's just pi r squared, right, where r is the radius of the wind turbine blade. And so the power that you get from wind or water, it's the same formula. It's 1/2 rho A V cubed. Okay, so let's break down what each of these variables is. V is going to be the speed of the fluid. All right. A is the area swept out by the propeller. All right. And rho is the density of the fluid. Okay, so if this was water flowing by the wind turbine, the density of water is 1,000 kilograms per cubic meter. The density of air is around 1.2 kilograms per cubic meter. Okay, so air is less dense, right? So in order to produce a certain amount of power, you need big, gigantic turbine blades. Okay, wind generators are huge; they're enormous, and so we have to sort of compensate to produce a reasonable amount of power. We have to compensate for the low density of air by making the blades sweep out a huge area, and because air is lighter, it is able to flow faster than water. Okay, and then of course there is an efficiency factor out front. Okay, so this is the theoretical maximum, and then we always multiply that by the efficiency. So what causes the efficiency of a wind turbine to be lower than the ideal? Well, if you think about it, it cannot extract. So what's happening is you're extracting the kinetic energy from the wind, all right? And you can't extract all the kinetic energy from the wind, because if you extracted all of the kinetic energy from the wind would just be stopped behind the wind turbine, and that would create like a traffic jam, and no more wind could flow, no more air could flow past it, right? Because it would just come to a dead stop. So you'd have this traffic jam immediately after. So what you have to have is you have to have flow on the opposite side, on the on the leeward side, I think that's right. Yeah, it's the leeward side. That's always a crossword puzzle clue. It would be like sheltered from the wind is leeward. Okay, so the downwind side, also known as the leeward side, is going to have not air that is at rest, but just air at a much lower speed. So we don't extract all of the kinetic energy. Otherwise, the air can't continue to move through the turbine. All right. So, and then I did want to talk a little bit about electrical power generation. Just so you know how it works. Electrical power generation involves, and this is non solar panel. So solar panels produce power in a completely different way. Okay. So for example, solar panels produce DC electric current, whereas the standard method that we've been using for a long time produces AC. All right. So this is the AC version. And basically what you have to do is you have to spin a turbine. I can never decide if I want to say it turbine or turbine because I've heard it said both ways. My gut is to say turbine, but people who work in dams and stuff say turbine. So I don't know. I keep switching back and forth. I can't keep it consistent. Basically, if you spin a turbine in a magnetic field, it will produce electricity. All right. So you have to spin something in a magnetic field, and then if you take AP Physics C or the second year of IB Physics, you'll learn why that is. But this will produce electric current. Okay. And so the major question is, the only difference between different methods of electrical power generation is what is doing the spinning? That's the only difference. Okay, so in hydroelectric, it's water doing the spinning. In wind power, it's wind the kinetic energy of the wind is doing the spinning. If you have like a regular coal power plant, so what if we have like a fossil fuel power plant? What you have is you have what's called a boiler. Okay. So this boiler is filled with water. All right. And you are heating up the boiler using fossil fuels. You're burning fossil fuels. So I'll make this look like a campfire or something. It's heating up the water to the point where it boils, and then it produces steam as a result of that. Hot air rises, so the steam rises, and there is a propeller blades in the path of the rising steam, which causes it to spin, and that spinning produces electricity. So it's the kinetic energy of the rising steam that spins the turbine. So we get electricity from that. And then this steam continues to rise, and then it goes through like what's called a condenser, where it so this is a condenser where the steam is brought into contact with something cold. So, for example, a power plant might be built next to a river, and it'll run river water over the condenser pipes. And so that'll cause the steam to recondense into water, okay, by the time it gets back to the boiler. And so it's a closed system, so it recondenses into water, and then it's just boiled again. So here's the turbine. So why does it need to be a closed system like this? Because you want the water to be pure. Because if the water has contaminants in it, that's going to cause corrosion in all the piping, and that's not good. So different types of power plants are just using different things to heat the water. Okay, if it is a nuclear power plant, then you're using the energy of the heat generated by radioactive decay to boil the water. If it's a coal plant, you're using the burning of coal to boil the water. If it's a natural gas plant, you're using the burning of natural gas to boil the water. Okay? So the only thing that's different between all these different power plants is what are you using to boil the water? Is it something good or is it something bad? All right? So that is my lesson for today, and I will see you in the Zoom room.